Yeah, I know. I gotta learn to talk faster. Okay, this is an online Smith chart where you just plug in values and it plots the stuff for you. Basically, the Smith chart was designed for solving transmission line problems. It was, I believe Mr. Smith worked for Bell Labs or AT&T, one or the other, and came up with this because they did a lot of long distance transmission line stuff. Essentially, all it is a rectangular coordinate system where they fold the vertical axes that go to infinity back onto themselves at infinity with the real axis. So it's sort of the assumption, and I think mathematicians, excuse me, assume that plus and minus infinity are the same point. I mean, it's kind of, who knows what it is. So these infinities are all the same point. So whether it's the real infinity or the inductive or capacitive reactance, it's infinity, they're all at the same point on the chart. So it makes it a circular chart. Therefore, all the lines that would be vertical are now circles that go back to infinity. And all of the horizontal lines that you would see crossing the vertical axes now become arcs, just because I wrapped it around into a circle. So I still have the intersection of what were the vertical and horizontal lines, except now it's the intersection of a circle and an arc instead of a horizontal and vertical line. The one thing that doesn't change is the horizontal or resistance axis. It's still a straight line, and it goes from 0 to infinity, with 1 being in the center. So we can normalize whatever impedance we want to work with by dividing everything by that impedance. So if I'm going to work with 50 ohms, I divide everything by 50. So 50 ohms itself comes out as 1 on the real axis. And all my reactances are also divided by 50. So they're similar numbers. And then when I'm done, I multiply everything by 50 or whatever number I use to get back to the real numbers. That way, the chart is kind of universal. Doesn't matter what impedance I want to use. And that's what this chart talks about. So if I was going to plot 50 plus J100 on this chart, I would plot it as 1 plus J2. Makes sense? Right. So how is a Smith chart normalized? Okay, so where I normally would have vertical lines representing different resistances, constant resistance along that vertical line, they now are circles because they're all folded back to infinity. Because each one of those horizontal or vertical lines, excuse me, would go to infinity. That's why it curves back. On what would normally be the vertical lines, the horizontal representation of 1, 2, 3, 4, instead of being horizontal, now become arcs that go back to infinity. So all we've done is kind of mush it around where this circle, okay, any place on that circle is a normalized 1 ohm.
50 or whatever you're using.
Right. Any place on this arc, which is inductive still, is going to be 1 ohm reactance, a plus J1. So this intersection would be 1 plus J1 or 50 plus J50. If I was doing the same down here, it's going to be, 1 minus J. So you still have inductance on the top half and capacitance on the bottom half. Smith charts are simple. Whoop.
Yeah, sure.
And that's an easy one. What coordinate system is used in a Smith chart? What are the two families of circles and arcs that make up a Smith chart? Charlie. In figure E9.3, what is the only straight line shown?
No.
Yeah, told you it was easy. Okay, so the arcs are constant reactance and the circles are constant resistance. The outer circle, which would be your main vertical axis if it was your y-axis, if it was a coordinate, is called the reactance axis, which is what it would be in the coordinate system, except now it's just a big circle. As I go around that circle, from 0 to a quarter wavelength, because remember when we did a quarter wave section, if I had it shorted on this end, it was infinity on the other end and vice versa. So as I go in that direction, it's showing me the electrical length of that quarter wave section as I go along. And come back this way, I'm going from an open back to a shorted. And I'm on the capacity part. And it's also on some Smith charts, you'll actually see divisions along that outer circle showing you the fractions of wavelength. So one of the things you can figure out is how long, when you're doing a stub, where you are on that outer circle tells you the electrical length of that stub that you're trying to calculate. So what do the arcs of a Smith chart represent? What's the name for the large outer circle? Okay, so we can calculate impedance along a line. So if we're doing like the 8th wavelength or something, you can figure out what that impedance would be, depending on what's on the input. You can calculate SWR. All you do is you have to draw a circle. If you if this is 1, and I come over here to, I don't know what they got on the chart. But let's say I do 2, and I draw a circle with 1 as the center, then any point on that circle would be an SWR of 2. So depending where things intersect the SWR circle, I can tell what the SWR is going to be. Which of the following can be calculated using a Smith chart? Which of the following is often determined using a Smith chart? Charlie. What third family of circles is often added to a Smith chart during the process of designing impedance matching networks? Alpha. Yeah, trying to help people with short-term memories.
About one.
One of the other applications is determining the length and position of a stub that we talked about. And on most charts, there's wavelength scales, which I mentioned, that go around the outside. So it's showing you the fractions of a wavelength as you travel along that outer reactance axis.
From 0 to infinity.
Right. From 0 to infinity is a quarter wave around. So it's a half a wave around the whole circle. Because remember, a sine wave repeats itself. It's just positive and negative. So the only thing I can compute the electrical length of a stub. All I have to know is the velocity factor to find out what the physical length is. So when I come up with the electrical length, I just multiply or actually divide by the velocity factor to find out what the physical length is. Or multiply, excuse me. Because it's going to be shorter. So all it can tell you is the electrical length. You still have to know what the velocity factor is to find out what the physical length needs to be.
Is that on a scale in there somewhere?
Which?
The length, electrical length.
Yeah, as you go around the outer circle, it's fractions of a wavelength. That's the electrical length. So when you do this, you'll intersect that outer ring at some point, and that is the electrical length that needs to be. Anywhere from 0 to a quarter wavelength. Which of the following is a common use for a Smith chart? Well, it can't be both.
Oh.
Oops. In what units are the wavelength scales on a Smith chart calibrated? Yeah, see, they threw antenna in there. It's not an antenna, it's transmission. Whoops. Boy. Okay, so we talked about how to normalize what the coordinate system was with circles and arcs. The only straight lines resistance axis, the outer circle is a constant reactance circle. um, or axis, I should say. And you can draw SWR circles, which are a constant SWR. So any place that intersects that SWR circle that's what the SWR is. And wavelength scales are on the outside as fractions of electrical length. So it'll be, I forgot how they label them, whether it's lambda divided by something, maybe, or it could just be numbers.
It's off of the wavelength scale.
Yeah. So I told you that was a short one. It was the easy one, right?